All right, here we go. So we're going to talk about light today. Those of you that are seniors would have had some of this when you were freshmen in physical science. The rest of you didn't have physical science. And I'm hearing every day about how we wish we did. Yeah.
Is this on mic?
Yeah.
Oh, good night.
You know what classes were?
The big old packets.
You will be able to see that. So what I'm doing now, these are your resource packets. And I know they're not stapled, but I printed them from my computer, and I just went ahead and made sure that we had enough copies for everyone. In the copier, I don't know how to make it staple because I'm not smart enough to, function with technology. So I didn't staple them. But feel free to staple them. I did wash sanitize my stapler from the last class. Feel free to use hand sanitizer after using the stapler if you're concerned.
Caleb, you take the longest staple of anyone I've ever met.
Every
Every paper I've ever been behind you on, I feel like this guy was you for 30 seconds.
Make sure you put your name on your packet.
I'm shaking. Got it.
This is a rough group to have at the end of the day.
What's up, Dave?
Yes.
Really looking forward to it. You are literally the perfection of all these things.
My dad.
Okay, so I want you to make sure you put your name on it, and then I want you to flip to the back of the second page.
Oh no, I can't see. I stapled it too low.
Well, I guess I'll let you have another staple.
No, it's okay. I don't want to rip it all out.
The back of the second page.
Yeah, that's that.
Okay. So let's start our discussion, and then we're going to reference the back of the second page. You remember that?
I remember this.
There's no way.
I know, right?
There's no way. Students don't remember things from one class to the next. Somebody yesterday dropped their calculator and it broke the screen.
Oh no.
They had to get a new calculator. All right, let's get started. Maybe. Thinking. Okay, here we go.
I remember this one.
Stop it.
This is great.
Okay, so for some of you, you probably have seen something like this, but I've never taught it to you, and I'm not going to assume that we remember things from a different class. So I'm just going to go ahead and go over it with you. This is the electromagnetic spectrum. The electromagnetic spectrum. And it contains all the different types of waves that we classify, and we put it on a spectrum. Now, a spectrum is something that's continuous. It doesn't have like a starting and an ending. And if you look up here at the little rainbow that we have, that is an example of a spectrum. One region kind of blends into the next. There is no distinct boundary where it starts and ends. That's what a spectrum is. So we're going to start on this end with radio. These are waves. So this is a radio wave. And actually, it's just all communication waves. When we talk about communication waves, radio waves, the Wi-Fi is included in this. We are talking about waves that have low energy, or relatively low energy. And you can see here that this is low energy, it says low frequency, and long wavelength. And we've got this wave here. See how it's all spread out, stretched out? So when the waves are stretched out like that, they don't have a whole lot of energy. And these are low energy waves. The spacings, because they're so stretched out, their wavelength is long. And I'll show you that here in just 2 slides. Now, as we increase, we're going to increase in we move into the next category, which is microwaves. Not the boxes that you have at home. These are the waves that are used in a microwave to heat your food. So you know, you take out a frozen pizza, you put it in the microwave, and when it's done, the center is still frozen and the outside edges could sear off your skin. Right? We all are familiar with what I'm talking about? Yeah, well, that's better. But some people are just impatient. So microwaves, actually, they contain more energy. Radio waves aren't going to do anything to us. They're not going to heat us up. There are radio waves all around us. But if we were exposed to microwaves, it's going to start affecting us. The microwaves can be used to obviously cook food. They can be used to heat water. There's all kinds of reasons that we would use microwaves. But this kind of radiation, there's a lot of background radiation in space, and a lot of it is microwaves. Okay, so you can see that the waves are a little bit more bunched up here. As we increase energy, we are increasing the frequency and we're shortening the wavelength. In the next category is the infrared. So infrared are typically our thermal waves. Have you ever seen pictures of a home in the wintertime and you can see like around the doors and the windows, it'll look orange and yellow and red? Do you know what I'm talking about at all? Yeah. Some of you do? Or if you've ever seen the movie Predator or a movie with Predator in it and you look through Predator's eyes, he sees like, oh, there's some red stuff over here that's moving around, I'm gonna go eat that. Those are all infrared waves that are being detected. These are heat waves. These are the waves that we would feel, the energy that we would feel coming off of a fire. These are infrared waves. There's a lot of heat associated with those. And infra means below. So infrared is below red. The next category is the visible spectrum. And this is the only region of the spectrum that we are sensitive to, that our eyes can see it. It is below red. So if we follow it up here, you can see that the red is right next to the infrared because infrared is below red. Scientists are really not incredibly creative sorts of people. They're going to call it what it is. So the visible spectrum starts with red and ends up here with violet. When we order it from low energy to high energy, the colors of the rainbow have distinct amounts of energy with them. Red is the lowest type of wave, lowest energy type of wave, and violet is the highest. So these increase in energy, the waves increase in energy as we go up. The visible spectrum is really important to us, but that's because our eyes are sensitive. This is a very tiny portion of the spectrum. Very tiny portion of the spectrum. This region, it runs from 300 to 700 nanometers. That's not a whole lot of space, okay? But you can see that they're definitely bunched up closer together than they were down here in the radio wave region. And that means that we're increasing the energy, we're increasing the frequency, and we have shorter wavelengths. After the visible spectrum, or the visible region, we have the ultraviolet region. Ultra means above. So ultra, above, violet. Here's our violet part, and then we're above that. This is, this region of the spectrum is, have you ever seen a black light? There are some ultraviolet rays that are in the black light, and it kind of gives it that weird, like reflecting kind of white light. These are the UV rays that come from the sun that cook things, right? I don't know, do kids your age still lay out and tan? Yeah, so it was really big when I was in school. I had a lot of friends who thought that it was a good use of their time to go outside and lay out in the yard. They'd oil themselves up. I had a friend I suggested she use butter, and she was like, well, that might work. Like frying an egg. I mean, you literally go outside, you put on oil, you lay down in the sun, you let the UV rays cook you, and when you get dark enough, you flip over, right? These can be harmful for your skin. They're actually responsible for a lot of skin cancers. Some people are prone to them. My father-in-law every year has to have some skin cancer. They're not real tumors, but they're like some parts of his skin he has to have removed because he's just real sensitive to it. He's got this big hat he wears, it's kind of goofy looking, but whatever. So the ultraviolet rays, those are the same kinds of ultraviolet rays that we would see outside. UVA, UVB, there are a couple of others. The next category are the X-rays. X-rays are so energetic that they can pass through your skin and soft tissues and they hit your bone and they reflect back, and that gives us a picture of your bones. Which is really good because otherwise we'd have to like scrape off the skin and flesh, and we don't really want to do that. It's biohazardous material. Okay. Anyway, so X-rays, they can penetrate soft tissues. We can use X-rays to sort of like examine different depths of different types of materials, and they're a lot higher energy waves. The highest category, the highest energy category of waves that we have on the electromagnetic spectrum are the gamma rays. It's not like in Star Trek where you get shot by some gamma rays and you'd like totally vaporize, disappear completely. But gamma rays are very harmful. They're very, very energetic. They have a lot of energy. They have a very high frequency, and they have a very short wavelength. So you can see these are all bunched up together, and because of that, they do the most damage. Lucky for us that a lot of that is filtered out by our atmosphere, by our ozone layer. So it keeps us pretty safe, but we do have to be cautious of some of our exposure. So that is the electromagnetic spectrum kind of in a nutshell. That was really fast. And now I'm going to move on to the next slide. Because again, remember I told you that yesterday, this discussion is going to start with our discussion of light. And I haven't completely made the connection yet, and we're going to see that here soon. But the electromagnetic spectrum is broken up into a lot of different categories, and we didn't always know about those categories. I mean, it's easy for us to see a rainbow in the sky, but how would we see any of the other regions if our eyes aren't sensitive to it? So a prism, have we all seen a prism before? It's a piece of glass. Usually it's in a triangle, and it's a long triangle, like a cylinder, but it's a triangular kind of, what would you call it? A prism. Okay. So the story that I was told when I was learning about this, and I can't verify the truth of it, is that during the time of Sir Isaac Newton, in the mid to late 1700s, I think, during the time of the Black Plague, Sir Isaac Newton he comes from a very affluent family, so they have a lot of money, and because of that, they had a country home, so they had a home in the city, and they had a country home, and that was a very common thing for people who had a lot of money. They would have several different homes, and they would travel between their homes, keeps them busy around a lot. Anyway, so during the Black Plague, Newton's family decided that they wanted to get away from the city, which was a good choice, right? Because they didn't know why people were getting infected with the Black Plague. They didn't know what was causing it, but they went to the country, and all of a sudden, nobody out there was getting sick. So anyway, while he was out there, he was studying something. He was doing some work in his study, and he had some prisms sitting on a table. And he looked at one of them one day when the sunlight was coming through, and he saw this rainbow. Which, that was not uncommon at the time. They knew that this happened. But what he didn't know, and he just kind of like put his hand down kind of next to it, just like this, and he put it down here by the red, and it felt warm, which was really odd to him because, then he starts touching all over the place. He felt this side, it was warm, and then he felt this side, and it felt cooler. So who knows how his brain worked? He was a genius, and eventually what happened was he was able to theorize that there's got to be something there that we can't see. We can see those colors, but it's not impossible for us to think about there's probably something there we can't see too. So they understood waves at the time, and they understood that maybe there were these invisible waves that were coming off of here, and because they had different temperatures, that meant they have different characteristics. But the really important idea is that this was sort of the first place where they could say, this is a continuous spectrum. So it goes from one region to the next without a clear, this is the beginning, this is the end. And that was have something the scientists believed, because they could repeat this and they could feel the difference in temperature, they could measure the difference in temperature. So that was a really important idea, that it's called discrete. There's not a discrete beginning and a discrete ending. It's a continuous thing. And all the edges blend together. Okay? So, let's talk about waves. There are a couple of characteristics about waves that we need to be familiar with. And you can see that I have two words down here. I have frequency, or I have a word and a phrase. Frequency and wave speed. We'll get to those here in a moment, but I definitely want to label a couple of things. From this peak to this peak, that is the length of a wave. A wave is a repeating unit, and our repeating unit in this case, if I start at the beginning, is going to be that portion. It's just one up, one down, and when it hits that line again, that's our repeating unit. And we can see that that thing repeats here, and it repeats here. That is one wave. The length of one wave is a wavelength. Again, scientists aren't real creative sorts, they're just going to call it what it is. It's the length of a wave, so they're going to call it a wavelength. So from that peak to that peak, that's a wavelength. From this peak down here to this peak down here, that would also be the same wavelength. The same distance. It's how big the wave is. It's a measure of how big the wave is. Now the symbol we use for this is that. It is the lowercase Greek letter lambda, and that's the symbol we use for a wavelength. That I've heard referred to as an upside down Y, looks like a broomstick. Call it what you will, but if you look on the back of that second page, like I asked you to open up to, over under abbreviations, you'll see that this symbol is there, and next to it says equals wavelength. Now what's the unit they put right beside it? M for meters. It is a length, so we measure it in meters, or centimeters, or nanometers, or picometers, or kilometers, any kind of meter. All right, sort of the standard is meters, but depending on how big that is, we might change it to something else. So that's the length of a wave. There's another thing that we need to label, and that is it could be from this peak to the axis, it could be from this to the axis, it doesn't matter which one, they're all the same. This is referred to as the amplitude. And it is given the symbol of capital A. Amplitude is not listed here because it's not really that important for right now. Okay? Amplitude tells us about the intensity of the wave. So, if we're talking about light, intensity is, it could be dim, that means it's really short, that amplitude is small. It could be very bright, which means that the amplitude is much bigger. The wave is a lot taller. That's what we mean by intensity, dimness to brightness. If we were talking about sound, intensity means volume. So it'd be really, really soft if it's tiny, it'd be really, really loud if it's tall. Okay? That brings us to frequency. Frequency is a rate. Frequency is a rate. And it is how many waves travel in 1 second. So if I have, let's say that this is where I'm going to measure them, right here. Okay? If I want to know the frequency of a wave, I'm going to measure or count how many waves pass this point in 1 second. So I literally just count them. There's 1, 2, 3, 4. And if 4 waves pass in 1 second, then that tells me something about the rate. That is the frequency. So it's a measure of how many waves pass in a second. It's not the same thing as wave speed, which I have listed down here. It's not the same thing. But they're related to each other. So the symbol we use for frequency, and I'm going to put it up here in the white part, is the Greek letter nu. And I know on your packet, they have it listed as a V. It's not really a V, it's kind of like it's the font that distorts it a little bit. If you wanna correct it to this, that's fine, but this is the Greek letter nu. This is the symbol we use for frequency.
Oh, my goodness.
In some old textbooks, they'll use like a F in italics
I don't really know.
for frequency, but I don't see that nearly as often as I used to. So this is the Greek letter nu, we use that for frequency, and then what does it tell you frequency is measured in?
HZ.
Hz. Remember I told you it's a rate. So frequency, and I'll do this up here in the white part so you can see it, there are several units we can use. What it really is waves per second. It's how many waves pass per second. So if I was talking about the 4 that I counted, it'd be 4 waves per second. Sometimes people drop the waves part and they just use 1/seconds. So 4 per second. Some people, mathy people, use seconds to the -1. That's just an exponent rule. But the actual name of this unit is hertz. Not like the car rental place. I mean, it's spelled like that, but that's not what it is. Hertz is a scientist's name, and we refer to the unit of frequency as hertz, and the symbol for that is a capital H and a lowercase c. Okay? Capital H and lowercase c. So I want you, the next time you ride in a car, I want you to look at your radio, because when you change the radio station, you're tuning in a specific frequency. And radio stations are measured in megahertz, and it'll be a capital M, capital H, lowercase c. FM radio stations are. AM radio stations are measured in kilohertz. It's a K, and then capital H, lowercase c. But you're tuning in a specific frequency. All right? Questions about that one? All right. So then that brings us to wave speed. Wave speed is the speed of a wave. It's the speed of a wave. In all of these waves, we're going to use the speed limit of our universe, which is the speed of light in a vacuum. It's a constant value, it doesn't change. So we're going to assume that any waves we're talking about that are light waves, they are traveling at the rate that light travels in a vacuum. Okay? So, do you have any questions about this?
So the difference between frequency is that it's how many per second, and then the wave speed is just how fast it's moving.
So think about last year when we were measuring velocity, because this really is wave velocity, right? We start here, we end there, how long did it take and how far did it go? Frequency is, here's my point, how many waves pass in 1 second. So just the nature of the values are different, but they are very closely related. Frequency, wavelength, and wave speed are very closely related, and we're going to see that in just a moment. All right? Okay, so we were just talking about atoms yesterday, right? Isn't that weird? Okay, so the first thing I want you to do is I want you to copy this down in that empty space right here.
Copy what it says.
Yep.
It's almost with the phone. Oh, no. I can't draw. Or do whatever this is.
Well, if you grow up in Greece, this would just be writing, right? Think about that, isn't that weird?
actually mean a little vacuum.
Yes, not a cleaner, not a vacuum cleaner.
Oh.
Vacuum absence of matter. Vacuum absence of matter.
Why so specific? Cause when you kept saying that, I was like, if you don't.
Yeah.
We just decided, let's just, light through a vacuum swimming.
Let's go home and shine the flashlight under the
That's what I was
vacuum cleaner,
confused
turn it
about.
on, like, I don't know what's going on. Mrs. Foley was talking about it today. I'm not sure people will question it. I don't know. Okay, so, the next thing I wanna point out is that the speed of light in a vacuum, it is in the absence of matter, not a vacuum like a vacuum cleaner, it's a vacuum as in the absence of matter. The speed of light in a vacuum is this value, but it's already on your packet. So if you look in the box right here above where you wrote your formula, the top box on the left-hand side, the third constant there is C. It gives you the value, and it tells you it's the speed of light in a vacuum. So you already have it. You're going to be able to use these resource packets on your tests and quizzes as long as you don't take notes in them. As long as you only put in there what I tell you to, you'll be good. Next, I guess we have to talk about the picture because that's all that's left. Right? So, the title of this slide is electromagnetic radiation because light is actually not the correct term to use. The correct term is radiation. Radiation is energy, it can be matter, but it's also energy. And when we talk about electromagnetic radiation, we're talking about energy. So this picture is difficult to draw. And it is the best picture I can find, even though it's fuzzy, so I want to talk about it. But I don't expect you to have to draw it. It's hard to read on this background anyway. But this is a picture of electromagnetic radiation. This is a picture of what we call light. This is what it looks like. It's not truly just a single wave. It's two waves that are perpendicular to each other. And those waves are very specifically related, right? The red part that's going up and down, that's a changing electric field. So the electric field itself, it's growing and then shrinking, and then it's growing in the opposite direction and shrinking, and then it's growing and shrinking over and over and over again. The blue part is a magnetic field. This is where the name comes from, that electromagnetic stuff. Electromagnetic, that's where it comes from. It's electromagnetic radiation. And the magnetic radiation is doing the same thing, it's changing. And it's increasing and decreasing, but it's moving side to side. It's perpendicular to the electric field. And they are growing and decreasing at the same rate. Do you see how they cross that axis at the same time? So are you ready for what causes it? A moving electron. A moving electron. What?
No.
As an electric field changes, a magnetic field is generated. And as a magnetic field changes, an electric field is generated. So the two are tied closely together. So the wave itself is moving in that direction, out of the plane of the board. And the electric field is perpendicular to the direction. Oh, they're all three perpendicular to each other. I don't know if you can see this. It's a 3-coordinate axis. Have you ever seen one of those before? Okay, let me see if I can. So we have the plain old X and Y axis, right? That's the 2-dimensional Cartesian coordinate system that you use in math class. But what happens is in 3-dimensional space, we have to add another axis. So the wave is moving that way. Maybe the electric field is changing that way, and the magnetic field is changing that way. They're all perpendicular to each other. This is a, I just forgot what I was going to say. It's a typical 3-dimensional coordinate system. It's a traditional, I guess is maybe the better word. Isn't that fun? I can see you're all dazzled.
So, is When the electron moves, is that the only thing it creates is light? Like, is it every time? Okay.
Electrons are weird things.
I thought electrons moved all the time.
They do.